Alright, good night guys. So here we are back again. This part C is from exercise 8. I did this yesterday, but this wouldn't fit the page and I didn't want to just show this for another page. So today we started at exercise 12 and it asks us to show for A if this is a legitimate function, which means if it's considered a function, or part B, if what would you change in f so it works. And I realized that I didn't change f, I changed the set s for this to work, so I'm not sure if that would count as a correct exercise solution. So exercise 12, it asks if it's a function, and I say that it isn't because 2/3 is the same as 4/6, and they wouldn't be the function wouldn't return the same value for these numbers. And for exercise part B, I said that I would restrict the set S to so it can only be represented in the lowest form, like lowest division or they can only be expressed in one way, and I thought maybe the lowest form. And by lowest form I mean like the lowest form of 4/6 would be 2/3, and the lowest form of 6/8 would also be 6/9 would be 2/3. So everything would be reduced to this like essential way. I don't know what's the correct term for that. So next exercise 13. So prove that f defines a function from S to t, and what property and why does it work. So this is basically the reverse of exercise 12. And what I said was well, it's a function because a function is something that for any s it would always return some t, and I said that that happens. And this works because 2 and 3 would be we have a number 2 elevated to m and times 3 elevated to m. This would be the lowest divisors of a number that can be written this way, because like 4 can be expressed in 2 elevated to 2. So if this was a 4, then maybe we could get some problems, but in this way they are always the lowest form, and so they can always be divided to this form. Yeah, so that means that f of s would be always a unique t. Next exercise 14. I'm not sure what they meant by necessary and sufficient conditions, but they said that fs would be as times b, a times s plus b, and they wanted to and they asked when would f after f be identity s, which means s for the which means the identity of set s would be s, just the element s. So I expanded and I got I got as plus b times x plus b equals x, and I expanded again and I got to a second degree polynomial. So I used the second degree polynomial solver, root solver or something, the quadratic function, and I got this. So for sufficient, I would say that if s equals this, then this would always work, and necessary it would be that this one is equal or more than 0 if we are not counting complex numbers. And next exercise, exercise 16. These ones are a little bit more interesting. Wait, not 16 but 17. But for 16 we had to show that the inverse of f, the inverse of the inverse of f would be f, and here I say that f, if f is 1 to 1, then we have an inverse, and I just put an inverse on this and it worked. For exercise 17, I'm actually not sure, I'm kind of confused. They say that S is a finite set of finite sets with m elements, and m has to be more than 0. And they ask how many mappings can there be from S into itself. So first I thought, like, consider a set that goes from 0 to 10. Well, you only really have one way that I can think of, that for each element you would get an element from 0 to 10 and all of them, which would be the identity function. But if we do, for example, negative 5 to 5, we could do the function f negative s, and also the function fs, and they would both work. But in this way I'm assuming that they can't be sorry, I'm assuming that this is the necessary condition, so there has to be always at least one, and sometimes there isn't more than one, so I'm just going to say one, which means there can't always be two ways. And I'm saying this not because I proved that there can't be more than one way that a function returns, like for the example 0 to 10, I can only think of the identity function, so f of 2 would return 2, f of 5 would return 5, and so on. And I really can't think of any other, so I just use that as a kind of a proof. And yeah, so here I say 1 because you have to have m returns, m different returns if you have m elements, so that it's into itself, and also those function f returns would have to be inside the set S. This infinity is because, like, I don't know, maybe there is some formula that you can put a set from 0 to 10 with a random function that returns from 0 to 10, like, and that isn't identity. And if there is more than one, if there is a function like that, then there's probably a lot of them, and I can't say it. Exercise 18, it's the same as exercise 17, so S has to be into itself, but has to be a mapping. Function f has to be a mapping into itself, but this time, how many one-on-one mappings are there? So I say, let's say there is a set from 0 to 5, from 0 to 5. Wait, from 1 to 5, yeah, so my example looks better in my head. And you get like f of 1. Well, f of 1 must be a number between 1 to 5, but it can be the f of 1 can be 1, 2, 3, 4, or 5. So for so let's do it this the other way. If there is a set from 1 to 5, there has to be a 5 from one of those, and only one. So we have 5 options for first one, then we have 4 options for the second number, and 3 and 2 and 1. So that would be m factorial. I think this symbol is called factorial in English. So there are m factorial mappings. For exercise 22 I couldn't solve this, I don't know. They say that S is a set of all integers and ABC are rational numbers, and they want to ask on what conditions, like on what A, B, C, can we define a mapping. And this is the formula: A s elevated to 2 plus B times S plus C. And they give a hint that is 1/2 of S multiplied by S plus 1, and this gives this result, which would be A equals 1/2 and B equals 1/2. This is the I think this is the something like the square, like 2, like S equals 2, we would get 3 plus times 2, which was 6. No, never mind. What I realized was an int would be k, okay, belongs to z set, and a divided by a would always return 1, so k times time 1 would be the integer set, but I really have no idea where to go with this one. So yeah, thanks for watching and goodbye guys.